So this is the first lesson on rotational motion, and we're going to work our way towards discussing torque and rotational mechanics. But first we really need to look at motion and how it relates to angular displacements rather than linear displacements. So linear motion obviously involves displacements, velocities, accelerations, and we know that velocity is the time rate of change of a displacement and is given by this equation. It's a very well-known equation. However, when objects move in a circular fashion or when objects take a curved path, instead of speaking about linear displacements, we talk about angular displacements. So here in this little diagram, we've got an object that's going to move from some position theta 1 to some position theta 2 in a given time t. And so we define an angular velocity in radians per second. And it's based on the change in theta over the change in time. In order to be comfortable with what we're going to do, the assumption is that you have a functional knowledge of radians and radian measures. If you do not, you should pause now and go and brush up on radians, what they are and what they're all about. It's really just another measure of angles, similar to degrees. Angular velocity, though, is defined as the time rate of change of angular position. So if a boy turns 45 degrees in 2 seconds, what is his angular velocity? And of course, we know that 45 degrees is equal to pi by 4 radians. And we can say omega equals delta theta over delta t, which is pi by 4 divided by 2. And our angular velocity is pi by 8 radians per second. We can, of course, simplify that, turn it into a decimal. There's no need at this point to do that. Angular acceleration, defined in a very similar way as linear acceleration. Basically, it's how fast velocity changes with time. And so if we're talking about angular acceleration, then we talk about how fast angular velocity changes with time. And there's the equation right there. So we can draw some parallels between linear and angular quantities. To start off with velocity, displacement over time, which we can relate to arc length if we're talking about angular displacements. So here is any general arc with some theta and some radius r. And of course, a particle traveling from the top of the arc to the bottom of the arc travels through a length of delta s, which is the arc length. So we can define the velocity as the arc length over time, which is really just the distance the particle travels. Well, our formula for arc length says that arc length is equal to the radius times the change in angle. And so now what we can do is we can actually link linear velocity and angular velocity. And they're linked by a factor of r. We can do the same thing with acceleration. Acceleration is equal to velocity over time. And if we sub this equation for the change in velocity, we end up with alpha. And we have a is equal to, the linear acceleration is equal to r times the angular acceleration. Now we're talking about an angular acceleration, and we should clarify at this point that we don't want to confuse our two different accelerations that are associated with angular motion. We have centripetal motion, which is uniform circular motion, where we have a is equal to v squared over r. Okay, that's a special type of acceleration. It always acts towards the center, and it causes uniform circular motion. When an angular velocity is changing, then we define an angular acceleration. Right? So these accelerations are different, even though they both deal with things that are moving in circular motion. To have a uniform circular motion, we need centripetal acceleration. So here's example 2. At low speeds, a fan blade is turning at 80 radians per second in the clockwise direction. The fan is turned up a notch, and now it starts to rotate at 125 radians per second. If the time to change the speed is 0.73 seconds, find the angular acceleration of the fan blades. So here's what we know. We know our initial angular velocity, we know our final angular velocity. Let's try and find our angular acceleration. Well, we know that angular acceleration is equal to the change in angular velocity over time. So we can write this as such and sub in our values. And what we get is 61.6 radians per second squared. So the angular acceleration, 62 radians per second squared.